All right, hello everyone. Today we're solving LeetCode 39 combination sum. So you're given an array of distinct integers candidates, and your target integer target return a list of all unique combinations of candidates where the chosen numbers sum up to the target. You may return the combinations in any order. The same number may be chosen from candidates in a limited number of times. Two combinations are unique if the frequency of at least one of the chosen numbers is different. So let's quickly look at the first example here. So our candidate numbers are 2, 3, 6, and 7, and we need to find what combinations of these numbers, and we can use each of these numbers in a limited number of time, add up to the target 7. So we can take 2 times for a grand total of 4, and then we take a 3, so 4 plus 3 is 7. Next, we can just take the 7, which adds up to 7. So our combination sum would have 2 possible ways to add up to 7 using these candidate numbers. So how to answer this question, we can model this with a decision tree, and that's why I drew this quick example here, and we're going to go through what it would look like. So let's say the first option, it's empty. We have chosen no numbers. And at this point, we can either choose the 2 or we can choose the 3. Let's say we chose the 2 first. So our array has 2 in it, and its sum is 2. We say we're doing depth first search, so we can say, all right, can we choose the 2 again? We can. So now we have 2 and 2 for a total of 4. We're not at our target yet, so we can just add 2 again. 2, 2, and 2. Sorry for the handwriting. So this is 6. We see that the total so far is 6. 6 is greater than 5, so that means that there's no number that we can add along this path that will lower our sum so far, right? Because we want the target of 5 and we're at 6. So that means we need to backtrack up because this is a fruitless endeavor. We go back up to the 4, where the total was 4, and we say, hey, we added 2 and that didn't work out. Do we have any other options? He says, yeah, we have a 3 left. So we can add 2, 2, and then 3. Same story here. 2 plus 2 is 4, plus 3 is 7. So we say, this is over the target. We can't add any numbers to reduce it to get to 5, so we have to backtrack back up. We're at the 4, and we said, well, we've used up all the numbers and nothing worked out, so we backtrack up yet again, and now we're at the 2. 2 basically says, hey, we chose the 2 and 2 again, so let's try something different because that didn't work out. We can say, let's choose the 3 because it's available. So we say 2 and 3, all right? 2 and 3 add up to the number 5. And 5 is equal to our target. So that means we want to save that somewhere because this is a answer. So 2 and 3. We know that adding anything to this path would increase it from 5, which we don't want. So we want to return back up. So now we're back at the 2 and we say, well, we've explored all the options. We added the 2 and we added the 3 and explored them. So now we have to go to the right-hand subtree. So what does it look like if we chose 3, right? So we say, hey, can we choose 3 again? We can. 3 plus 3 is 6. 6 is over our target, so we know we don't want to explore this path anymore. We recurse back up to the 3. And you might be thinking, hey, do we have a 2 to add, right? Why don't we add 3 and then 2? That would not be considered a unique combination. 3 and 2 and 2 and 3 are equal to each other. These are not unique, so we don't actually want to process that. So what we're going to do is when we're at the root of our decision tree and we go to the next number, we want to start the call at the next number. And when I get into the code, I'll explain it more, but think about it as we've already explored all possible combinations starting at 2. So when we explore the 3, we don't want to go back and add the 2 because we're at 3 here, right? So we only want to add numbers at 3 or in front of 3. In this case, there is none. So that's why we add the 3, recurse back up, and there's no other options. So the DFS call would end. And this ensures that we do not have any duplicates, right? So we would return 2 and 3, and that would be our answer. And before we continue, let's go into what the time complexity of an algorithm like this would be. It would be big O of n to the t divided by m. And we're going to quickly break this down. N stands for the number of elements, right? And the t stands for the target. And we divide it by m because M is the minimum number in the candidates because we don't know how deep this tree will go, right? So let's say the target was something like 100 and one of the candidates was like 1, right? That means we can go in the tree and add 100 times before we get to 100. And the recursion depth would be essentially target. So target of 100 divided by 1, which would be 100. So it'd be n to the 100th power, right? So hopefully that makes sense. And if you need to rewind the video, no problem. So now let's get into how we code up a solution like this. So the first thing I like to do is have a res variable, and that's just going to be the container that's going to hold all of our combination sums. Next, what we should do is create our DFS function. So we define a function and we're going to say def DFS, and it's going to take in a couple of things. The first thing we need to do is our combo, which would just be an array that's going to hold our current combination. Next, we need a start to know where in the array we should start iterating from. And lastly, a count. And the count is just going to tell us all of the numbers that we've added up to so far. So in this example here, this array here would be the combo. The count would be the current sum of the combo. So in this case, it would be 4 for 2 and 2, and here would be 2 for just having the 2. And our start index is, remember when I had this little arrow pointing here? Once we iterate through the 2, we know that we've already processed all the possible combinations starting at 2. So when we go to the 3, there's no need to go back and check the 2. We only want to look at elements at the current index and ahead of the current index to prune out duplicates. All right. So now that you know what all those things are for, let's go into the algorithm. It's a DFS function, so we know this is recursive. So we need a base case. So if count is greater than target, return. And if count is equal to the target, we have to append. So we say res.append combo and a copy of combo. All right, so let's go over what are these two things doing. The first one, if count is greater than the target, this is less than. If count is greater than the target, we want to return. So just like when we had the 3 2s, we have 2, 2, and 2. That adds up to 6. That's greater than the target, so we don't want to go any deeper. We're going to immediately return. And the second line here, if count is equal to the target, that means we've found a combination that sums up to the target, so we need to save it to our res. And we put the little, this means copy because arrays are stored by reference, not value. And we want to return after we found that. All right. Next, we need to have a function, or we need to have a loop that loops over all of the candidates. So for I in range length of candidates, and we want to start at the start. So in the first iteration, we'll start at 0. In the second iteration, obviously we go up and we'll start at 1. And just to quickly go over to match the code that we're writing to the intuition behind the problem, we're looping over the length of candidates. So as you can see, at the first level, we start off with 2, and then we went to the 3. And why we are adding start is because once we've explored this path, we looked at all of the possible combinations that start off at index 0, i.e. the 2. And once we go to the 3, we don't want to explore anything behind the 3 because that has been already computed from the last DFS call. Because if we did not do that, we'd start off at the 2, and 3 would go here and say, let's add a 3 and a 2, which is a valid combination, but it is equal to 2 and 3, and we don't want to do that. So it prunes out duplicates. All right. Next, what we want to do is say combo.append, and we want to take the current number we're at. So candidates at index I. So next we want to explore that path with the number we just added. So we say DFS with the current combo. Start is going to be I, and the count is just going to be whatever the count is plus the number we just added. So candidates at I. All right. And we keep I the same here because we can use the number an infinite amount of times. So once we're at the 2, we say, hey, we go one level deeper. We don't want I to increase up because we can pick the 2 twice or 3 times or an infinite number of times. So we keep I the same, right? Once we've explored all possible paths, we have to undo our work. So we say combo.pop, right? And if you don't know why we undo our work, once we've explored all the paths that start with 2, we need a fresh slate to add the 3. If we kept the 2 on here and never popped it off, how would we get a 3 all by itself? So since now that we did that, all we have to do now is actually call the DFS function. So we say DFS, and we're going to have an empty array as our combo. Our start's going to be 0, and our count's going to start at 0. And we run that, and we need to return res. So let's see. Hopefully this works. All right, and we solved the question. It's actually pretty efficient, so I hope you learned something new. Peace. Make sure to drop a like. Good stuff.